Hello, welcome to the fifth lecture of matrix method of structural analysis. What we are going to do today is we will review some of the concept of stiffness and flexibility. So, this is lecture 5. Okay, before jumping on to the definition of stiffness and flexibility and what does it mean in the context of structural analysis, let us try to understand through some demonstration. You see, take on a strip, on a channel. If I apply some load, for instance, if I apply some bending, then it may bend like this. Okay, that is the maximum bending that I can give. Now, take the similar thing, a piece of a paper, and apply the similar bending, and we can see that this is the kind of deformation it experiences. Then we say that this is more flexible than this. So, it is more stiffer, it is stiffer than this. The stiffness and flexibility, these two words we have used in different contexts, but and the meaning of stiffness and flexibility that we use in different contexts, here also the meaning remain almost similar. So, its stiffness means, so essentially stiffness and flexibility of any body, any object is essentially is a measure of or the measure of its ability to deform when it is subjected to certain amount of load. In this case, its stiffness is less, its flexibility is more, but in this case compared to the previous one, it is stiffer, but its flexibility is less. Okay. Now, let us start today's discussion with the last slide of the previous class. You remember in the previous class we discussed there are three pillars of structural analysis. One is equilibrium, which tells you how the different forces are related to each other, internal and external forces are related to each other. Then you have compatibility on the other end. The compatibility is now when a structure undergoes deformation, then how what is the relation between the deformation at various point of the structures, how these deformation is related, deformation at a particular point is related to the deformation at the other point, and whether the boundary conditions at the constant that is given to the structure, they are being satisfied or not. So, that is something we call compatibility. Now, the third pillar, which essentially is a relation between equilibrium and compatibility, is the constitutive relation. So, now, when we talk about constitutive relation, there are two important ingredients of a constitutive relation. One is stiffness and another one is flexibility, and that is what we are going to discuss today. Okay. Let's consider one example. One is simply supported being subjected to any distributed load. Then we know then this is the bending moment and this is the shear force of the beam. Now, these steps, this is statically indeterminate structure. So, we can just apply the equilibrium conditions to find out bending moment and shear force. So, this is the problem of statics. Okay. So, the problem of statics, the equations that we use is the equilibrium equations. And what are the variables? Static variables. Static variables are here in this case bending moment and shear force. Okay. Now, all the force variables. Now, then suppose under this load the beam deforms like this. Now, the deformation at say for given at point A rotation is theta, at point B rotation there will be another rotation theta b, then at any arbitrary distance from A deflection is y. So, now theta x, y and theta b, they should be such that the conditions and continuity that the beam must have, these values of theta x, y x and all these deformation variable, they should satisfy them. And this is called compatibility, and in this the process of finding this deformation is called the kinematics, and the kinematic variables are in this case you see it is what is the radius of curvature, then what is the deflection at any point, what is the rotation at any particular point. Now, so this is one pillar, this is another pillar, and then what constitutive relation does is the constitutive relation gives how these two different variables, mean the static variables and the kinematic variables, are related to each other, and that is the main purpose of constitutive relation. Okay. So, constitutive relation is essentially a relation between your static variables, in this case moment and shear force, and the kinematic variables. Now, at this point one point I should make, the constitutive relation or constitutive modeling is a separate branch in mechanics, or I would say the very large branch in mechanics. So, we will not go into detail of those constitutive relation here. Whenever we talk about, whenever we say constitutive relation, it implicitly means the relation between force and displacement. When we say force, it accounts for everything, force and moments, and when we say displacement, it accounts for everything, displacement, rotation, everything. So, force is the static variable and the displacement is the kinetic variable, and constitutive relation, at least for the present context of this course, is the relation between force and the displacement. Okay. Now, take some example, take a spring, linear spring, and which is applied to a force P, and then under the action of this force P, suppose x is the displacement, and then we know the relation between force P and the displacement, and the relation is P is equal to kx, where k is essentially P by x, which is force per unit deformation, and then k is called stiffness of the spring. Now, if we plot the load displacement curve, before that, what is flexibility? Flexibility is the just opposite of stiffness. So, in this case flexibility will be deformation per unit force, and if in this spring the flexibility F is equal to 1 by k. So, this is stiffness and this is flexibility. Now, this is very straightforward for a now then one thing is very important here. Whenever we talk about stiffness and flexibility, they do not carry any meaning until and unless we mention that this stiffness or this flexibility they relate which force to which displacement. For instance, in this case the force is this, and in this case say force is this and displacement is force is this and the displacement is this. So, when we say that it is force into displacement, when we say the k is the stiffness and flexibility F is the flexibility. So, it means that they relate, F and k relate P and x. So, every time when you talk about flexibility and stiffness, as I said, they are not just absolute word, they do not carry any meaning by itself. Always we have to mention along with them that these stiffness and flexibility relate which force to which displacement. Okay. Now, let us see some example. Take a propped cantilever beam, and suppose we apply a moment MAB. Moment MAB, because moment is applied at A in a segment AB. Now, due to the action of this moment, this beam may undergo deformation like this. So, we have theta A is the rotation at end A, B being the fixed end, there is no displacement, no rotation at B. So, theta A is the displacement, but also we know that when we apply a moment MAB, there will be a resisting moment at B, suppose that is MBA. Okay. Now, we already know how to solve this structure. We have learned that in structural analysis 1. Suppose, and the solution is something like this. MAB, the relation between this force MAB and relation between this and this theta is this, where E is the Young's modulus of AB, I is the second moment of area of the cross section of the beam AB, and LAB is the length of the beam AB. And similarly, we have we have moment B A is equal to this. Okay, that is how the MBA is related to theta A. Now, then what we say is then MAB can be written as this, and where Ka is equal to the entire thing, Ka is equal to the entire thing. Similarly, MBA can be written as KBA into theta A, where KBA is equal to the entire this entire thing. And then we say that KAA and KBA, they are stiffness. Now when we, as I just now I said, just stiffness is a term do not carry any meaning. Stiffness term do not carry any meaning. For instance, in this case the stiffness Ka, there it relates force MAB and theta A, but in this case KBA, this relates theta A and MBA. So, that is why it is written as KAA, means it relates displacement at A and the force at A, it relates displacement at A due to the force at B. Okay. Now, similarly, then what would be the flexibility? Flexibility would be just in this case the flexibility will be 1 by Ka, which will be L by 4 E I, and similarly in this case it will be 1 by K B A, this will be L by 2 E I. Okay. Now, so this is stiffness and this is flexibility. Okay. Now let us see some more example. This is another example. Suppose we apply a load MAB for moment MAB here, then it undergoes deformation like this, theta and theta B, the deformation rotations at A and B respectively. And then again from structural analysis zone, these are the solutions. Okay. There will be no bending moment at A generated, because this is hinge support, and MAB and this theta and this theta related to it, related like this. Now, we write MAB is equal to Ka into theta A, where Ka is equal to this, and then similarly MBA is equal to KBA into theta A, where KB is equal to 0. So, these are stiffnesses, this is stiffnesses. Okay. This is stiffnesses, this is stiffnesses. Now, you see there is a reason why we know that MBA is equal to 0, but in spite of that there is a reason why I wrote KBA is equal to 0. Explicitly put a star marks here, will come what happens when stiffness becomes 0, what is the physical significance of that. Okay. So, similarly by 1 by stiffness you can get the flexibility, but don't, you may ask this question that 1 by K, these give flexibility is infinite. As I said, there is a purpose why I intentionally wrote KB is equal to 0. We will come to this point again in this course, and we will see what is the physical significance, what is the interpretation of stiffness being 0. Okay. So, now, so again in this case when we say that it is KAA always means that it relates force theta displacement theta A and moment theta BA, theta AB. Let us see one example where in the previous example we had just one force. Now, here suppose we have two forces in the same beam, we have moment at A and force P at the mid span. Okay. Now, if we know just before writing the flexibility and stiffness coefficients for this problem, let us review the principle of superposition. If you know, the principle of superposition is, as the name suggests, that if we have a problem like this, and again it is only applicable for a linear system, as long as your force displacement relation is linear, you can apply this. And then this entire problem can be divided into 3 parts, and then So, you can take the effect of individual load separately and then combine them to get the total effect of the entire loading system. That is what the principle of superposition is says. So, we just superimpose the effect of different components to get the component of the exact actual loading system. Now, we do the same thing here, and suppose in this case it is a delta 1, delta 2, delta 3 are the 3 displacement for 3 separately computed, then the total displacement at C due to the effect of entire load will be d 1 plus d 2 plus d 3, and it is applicable as long as your displacements are small, load deflection relation is linear. Okay. Now, so again go back to the previous problem. Similarly, we can apply the principle of superposition in this case and divide the entire problem into 2 parts. One is just the moment applied to this, and this is the theta A and m is related, theta A and m is related with this, and then we can have, and suppose that is written as m into alpha A, where alpha A is equal to L by 3 I, and again delta B A, which is displacement at B, is equal to m L square by 16 E I. Again we can write is m into F B A, where F B A is equal to this. So, because due to the action of this moment m at A, we have displacement at A and we have deflection at delta, and this rotation and the deflection is related to m as this. Okay. Now, the next consider the second part. Second part is the another load this. So, if we apply a load P here, again displacement is rotation at is theta A and displacement is theta B B. Now, please note the notation used. Theta A means it is rotation at A due to the moment or due to the force at A. Theta B A means it is the displacement at B, delta B A, displacement at B due to the force at A. Now, here theta A B means it is displacement or rotation at A due to force at B, and delta B B means it is the displacement at B due to the force at B. Now, again from structural analysis 1 we know the relation, and this is the relation how the theta A B and delta B B related to P, and then these are coefficients. These coefficients are, if you look at carefully, these coefficients are flexibility coefficients. Why it is flexibility coefficient? Because alpha A is essentially the displacement for unit force. When m becomes 1, then alpha A becomes theta A. Similarly, when m becomes 1, delta B A becomes F B B. So, these are the displacement, these are the flexibility coefficients. Now, again coming to that point, I am repeating that point again and again, because it is very important to understand or put that in mind, that whenever we talk flexibility and stiffness, it is always associated with a pair, force and the displacement, and which force we take and which displacement we take, depending on that we have different flexibility and stiffness coefficients. For instance, when we take force m for moment at A and rotation at A, your flexibility coefficient becomes this, and in a reverse way stiffness coefficient becomes the opposite of this. When we take moment at A and displacement at B, your flexibility coefficient becomes this, or the stiffness becomes 1 by this. Similarly, for this and this. So, now if we go back to our previous problem, the actual problem was, if you recall, the actual problem was this. So, this problem is divided into 2 parts. These are the 2 parts. So, in actual problem, so these are the effects of moment at A, these are the effects of displacement force at B. So, total effects will be, so total displacement, total rotation at A will be this plus this, and then total displacement at B will be this plus this, and that is what we can do. So, total rotation will be this and total displacement will be this, and if we substitute that, so these are the So, total displacement will be this plus this plus this, and total displacement will be this plus this, and total rotation will be this plus this. Now, if we write that in a matrix form, you see what we may get is, you see. So, total is this and total will be this. Now, can we, if we write that in a matrix form where we have say theta A and delta B, the entire thing we can write as something, and then we have M and P, and this becomes alpha AA and then alpha AB, and this is F BA and F BB, isn't it? So, this relation gives me the total theta A and total delta B. Now, this is also a force displacement relation. You see, it is very similar to spring, where we had just one force and one displacement component. Here we have just two forces and four displacement components, and this matrix relates the forces, which is M and P, and the displacements, which is theta A and theta B. So, this is again a constitutive relation. Okay. Now, so if we see, this is written in matrix form. So, this is written in matrix form. Now, one thing is very important here. In this matrix form, I will just, in the next slide I will substitute the value of alpha, AB, all these values, but you will see when we substitute that this matrix is a symmetric matrix, means the off diagonal terms are same. So, in this case F AB is equal to F BA. What does it mean? F AB is essentially your F AB is the rotation at A due to force at B, and F BA is equal to displacement at B due to the force at A. So, these are same. So, this is, if you recall, this is known as Maxwell Betty law of reciprocal displacement that you studied in, and this is very important because when we this is very important. This property is very important because when we derive equations for matrix method of structural analysis and see the properties of matrices, then we will see that symmetry is one of the very important property that those matrices satisfy, and we will also see what is the physical significance of those matrices being symmetric. Okay. Now, next slide we just substitute those values. If we substitute those values, if you see these 3L and 3L, these off diagonal terms are same. This is flexibility matrix and this is stiffness matrix. You see why it is flexibility matrix? Because if we make unit force, then this gives you the displacement. So, displacement for unit force, that is the flexibility, and in this case unit, when displacement becomes unit, and then for force for the unit displacement is essentially the stiffness. So, therefore, this is called stiffness matrix and this is called flexibility matrix. This is very important, and we can, this symmetry can be observed here, symmetry can be observed here. Okay. This is very important because this is the building block of matrix method of structural analysis. We will discuss these matrices, flexibility and stiffness matrices in detail as we progress. But in this case, but another important thing, you see, you have only two forces and four displacement components. That is why you have 2 by 2 matrices. But then if you apply another force here, if you apply another force here, and then if we consider the displacement at this point also, then we have 3 displacement, then the matrix, the stiffness and flexibility matrix, they become 3 by 3 matrix. So, size of the matrix it also depends on how many forces or how many displacement components or we are talking about, or in a way, or how many degrees of freedom that the object has. Depending on that, we have different sizes of these matrices. Now, these matrices are very important. This is called flexibility matrix, stiffness matrix. So, if you go back to the spring problem where we had just one force and one displacement component, we can write the stiffness and flexibility, those are scalar because they relate one force component to one displacement component. But then here when you have when we talk about various components of the forces and the various components of the displacements at various locations, and then we instead of a scalar, these becomes, the relation becomes a matrix relation. So, there the flexibility and stiffness are, they become matrices. Okay. Now, you see, so we stop here now. The flexibility, as I said, this relation, the matrix, stiffness matrix plays the crucial role, that is the building block of matrix method of structural analysis. So, we will discuss these stiffness matrix in a more detailed way for different kinds of structure with different scale, or different scale means whether it is a 1 dimension, 2 dimension, 3 dimension, what happens to these matrices. We will discuss those in details, but here for today's class the idea has been to review the stiffness, the concept of stiffness and flexibility, and the concept of stiffness and flexibility as a language, as an English word, or the meaning of stiffness and flexibility, the meaning of stiffness or flexibility in matrix in structural analysis context, they are also very similar. Okay, so we stop here today. Next week, what we do is we'll see. Now, again, we'll see, briefly review the different methods for solving statically indeterminate structure. We have just now discussed two concepts, flexibility and stiffness. Then which concept to use to solve a problem? Depending on that, we have two class of methods. One is force method and displacement method. Next week we review briefly the basic concept of force and displacement methods, and then once we do that, our review of structural analysis will be done. And then in the third week, we will be having brief review of the matrix algebra, and from 4th week onwards, we will start formulating matrix method of structural analysis for different kinds of structures. Okay, then I stop here today. See you the next week. Thank you.